Second. Okay, so this was an example we looked at, but we didn't really go into too much detail of the block on an incline like this. What do we know about the forces acting on the block?
Friction.
There is friction. What about big picture? What do we know about it? What must be true?
They're balanced.
They're balanced. Okay. Be careful there, Zinzi. The forces, there are some forces that are equal, but the best way to explain that is to say that the entire force diagram will be balanced once you break it down. Right? Some of the forces might not directly equal one another. And we'll talk about what that means right now. So, let's draw a force diagram for the block on the surface. Okay, so this is where you can start your notes here. Here is our surface. Here is a block. Help me out. What forces are acting on it? Gravity. Where does gravity point?
Down.
Straight down. We'll call it F, G. We're at the point now where we can start to abbreviate our forces. I'm not going to ask you guys to write out all of those forces in detail, because now you should have a good idea of what we're talking about. Lindsay, you said friction. Which way would friction point?
That way.
Tell me in relationship to the surface. Is it going to go with the surface, against the surface, parallel, perpendicular? Parallel to the surface, away from where you would expect the block to go, right? How's that look? Pretty good?
Perfect.
And that's force of friction. That's all you need to write. What's the last force that's acting on this block? The normal force. And what is the definition of the normal force? Where does it point? Julie, is it always up? Right. You gotta check yourself there. Most of the time it's up if we're standing on a level surface. In this case, it's a unique one. It's no longer straight up, it's, well, let's be real clear with how it points. Where is it? It is slanted, but let's be super clear about what slant. It's what to the surface?
Parallel. No, it's perpendicular.
Perpendicular to the surface. So if this is the surface, the normal force points perpendicular.
Perpendicular.
Like that. And that's our sign for force normal. Ooh, my gravity force is a little janky, but that's okay. All right, and then the question is, our question that we're going to answer is, how do these forces balance? Because we know they should, right? Using our information that we've learned so far, we know that these forces must be balanced because there is no what? What's making us understand that there's no unbalanced forces? What would an unbalanced force cause? What would an unbalanced force cause? There's only one answer. No.
Acceleration.
Acceleration, right? Be very careful there. It's not just motion, but acceleration. It needs to be super clear. Okay, so we know it's not accelerating. We know these forces must balance. We don't really know how we're going to think about it. Well, you don't have to write this one down. The reason that we can say that forces balance pretty easily before is because we might have had a force diagram that looked like this. These ones are balanced, and these ones are balanced. Let's do a quick comparison. Why is it easy to say that those ones are balanced, but we can't say very easily that the other one's balanced? Maybe the same thing about that. I have a buffer back here. Let me say it again. Why is it very easy to say that these are balanced here, but it's not so easy there?
Because of the equality on one
Okay, let's think about that. Where can I make equality marks here though? Can I make any equality marks on this one yet?
No,
No. Why is it more difficult?
because there's forces going in a whole bunch of different directions.
That's a pretty good answer actually. That in this case, let's see if this helps. If I drew here, we'd say, wow, that pretty fits a good XY coordinate system. Right? It fits right on a good XY coordinate system. Is there an XY coordinate system I could draw here that would fit all these forces?
No.
No. There's not. But don't worry, we can fix that. If we think back to coordinate systems in the class, we said whenever there's an incline or a tilt, we want to draw our coordinate system at a tilt to fit that surface. That's going to be our best case scenario. We fit that surface with a coordinate system. So let's go ahead and just do that. Let's say our coordinate system is going to look, remember these are parallel and perpendicular, so these should be right on the coordinate system. This is our x and our y axes. Great. We got two of the forces right on the x and y axis. What's our problem force? Gravity. Gravity is no longer along one of those axes. So we can't say there's no force down here to counteract the normal force. There's no force over here to counteract the friction force like this one really neatly shows. So how do balance? How do these forces balance? How do we know they balance? And the answer lies in our friend trigonometry. My friend trigonometry. I love trigonometry. So, in order to solve this, we must use trig. Okay, I'm going to draw a very common shape that you'll see in trigonometry. What do we call this? A right triangle. A right triangle. Alright, now this is your time. Your time to shine. If I call this right here angle theta, so remember that little sign represents a number. It's a variable. It represents 30 degrees, 40 degrees. Say it could be like 2 pi, right? It could be radians as well, but we'll just keep degrees. That's our angle. Can we dig deep into our trig brains? Can you guys start to name some stuff about this triangle? Rylan, what do you remember?
Isn't it like
That's one way we could think about it. Let's talk about the sides first. Can we give some names to the sides? Hypotenuse. And okay, you're gonna fill it. So we got a hypotenuse. We're gonna give it away. Okay, now here, let's make this mistake once if we're gonna make it. And let's be really good at not making the mistake. How do we know the difference between opposite and adjacent? Does anyone have any tricks?
Opposite is always across the angle that you're looking at.
Okay. I think about it in terms of the adjacent. I always say the adjacent is the side that touches the angle. And so you can think of it both of those ways. The opposite one is away from the angle, or the adjacent one is the one that always touches the side of the angle. So this would be our adjacent side, and this is our opposite side. Right? Now remember, if I decided to say the angle was here, then our adjacent side would be here and our opposite side would be there. Right? That can flip really easily. So don't get right triangles in this type of trigonometry. You need to take it in context. Know what kind of example you're looking at. Okay. Great. Hypotenuse, opposite, adjacent. You guys are gonna help me finish this? Here. If I write sine of theta, I write cosine of theta, and I write tan of theta. Elizabeth, can you tell me what sine of theta is going to be? Do you remember?
Opposite over hypotenuse.
Great. Opposite over hypotenuse. Anyone want to go for cosine? Opposite or adjacent? That's up there, but it's not cosine. That one's tangent. We can put tangent in. Opposite over adjacent. Adjacent, I heard it. Adjacent over hypotenuse. S-O-H, so, C-A-H, ka, T-O-A, toa. SOHCAHTOA, right? You guys remember that one? Or have you guys gone over this in trig?
Yeah.
Okay, great. So this is all review for you guys. We can keep moving. All right, so this is where we're going to really understanding how these relationships work. I told the other class, you don't need to memorize a whole lot of things in math. You usually can look it up, but memorizing these is a really helpful thing. It'll save you a lot of time. So if you can spend some time to just memorize these, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. It'll save you a lot of thinking. They're in your brain already. I'm going to do a little trick here. Actually, it's not a trick. It's just algebra. I'm not going to tell you why I'm going to do it yet, but we'll see it in a minute. I'm just going to do a little bit of rearrangement. So remember, these are all variables. That's the opposite side, that's the hypotenuse, that's the sine of an angle. So we can rearrange them just like if there was A, B, and C. We could multiply C to one side, we could divide the other one to the other side. We could switch them all around however we really want. That's the beauty of algebra. So, would you agree if I wrote that the opposite side should equal the hypotenuse multiplied by sine theta? Take a second to look at that. All I did was multiply the hypotenuse to that side. Right? I just multiplied the hypotenuse to this side and I got a new equation. The hypotenuse times the sine equals the opposite. Okay? Did I lose anyone there really bad? I'll show that.
Say it again. Do it again.
So here's an easy way to think. If we replace this as just A equals B divided by C, right? Just, and you multiply both sides by C, these C's cancel out, you have C times A equals B, right? See how I did that? You just are rearranging the letters. So this will be our C times A equals B. Okay? Just a little rearrangement with algebra. So what would be, can anyone show me that they really get it? What would be the same thing if I did it here? Perfect. Adjacent should equal the hypotenuse times cosine of theta. If you don't know these already, this is another way to just think about trig. That's all we're going to do for those. We don't need to do the tangent one. Okay. How does this relate to physics? Well, trig is very helpful when it comes to vectors. So any vector can be broken into components. Components is a new word. It just means vector pieces. You can break one vector into two little vector pieces. So we call those components, vector components. Any vector can be broken into components. So let's look at an example. If this is here's my x and y axis. Always good to know where your x and y axes are. And let's say we just have a force that's not on that. It's actually 30 degrees 30 degrees on an angle from the x-axis. Well, that's not going to be very helpful if we try to, that looks kind of similar to what we got over there. We're off the x or y axis, we need to do something with it. My question is, for this one, and another question to help us answer our first question, how much of this vector points along the x-axis and along the y-axis? So does any of this vector point along the x and y-axis? And the answer is yes, it does. And how can we come to understand that? We treat the vector like a right triangle. Like a right triangle. So let's take it off of our coordinate system. This is our force. What side of the triangle does it look like this is, if we look over there? Looks like our hypotenuse. So let's fill in the other sides here. There's our right triangle, and this is our 30 degrees. Okay? Any vector can be broken into components. Let's break this into a component. Where might be a component, where do you think we can break it to answer this question? How much of it points along the x and the y-axis? We're going to break it so that the two pieces point right on the x and right on the y. And this is what it will look like. This is one of the components. This is another one of the components. Now let me be really clear. This red and blue is just this black vector broken into two pieces. I did not draw two new vectors. I just said we're going to take this one and we're going to split it into this and split it into this. It's its components. So this is just vector f broken into little pieces of vector f. What do you think we can call, one of them has to be vector fx and one has to be vector fy. What do you think this one will be? Y, right? If we're looking here, there's our y-axis. This will be vector f little y. And this will be vector f little x. Look at that. Look at that. Now we already said this this vector here is our kind of like our hypotenuse. What would vector x be or y be if our angle is over here? Opposite. Awesome, Christine. Opposite. And then that just leaves our adjacent side. Okay. We're finally getting back to what we need to think about. Now we know, we went over our trig here to help us understand that we can break vectors into pieces, and we used our trig to break this vector f into an fx and fy. So how much of it points along the x? It's this fx. How much of it points along the y? It's this fy. Now what if I said we knew what vector f was? That's what we started with. All we know is vector f in 30. Let's see if we can write fy in terms of f in this 30 degrees. If we look back to here, we can see that the opposite side should be the hypotenuse times the sine of the angle. Well, this is our opposite side. That should equal the hypotenuse of f multiplied by what?
The sine of 30.
The sine of 30. Beautiful. F sine 30. And this should equal the vector f multiplied by, not the sine of 30, but, what do you think, Carla?
I was looking at it, maybe writing it down a lot.
We use this one for the opposite side,
Oh,
times, not sine, but the adjacent side is related to what trig function? Cosine theta. So cosine of 30. So now if you knew what f in 30 was, you could figure out what this piece is by using that, and you can figure out what this piece is by using this. Right? So we now have it rewritten in terms of the two things that we started with. We have our components rewritten for those two things. All right. Let's go back to our original question. We're back here. How do we balance these forces? What do you think we need to do with Fg? What do we need to do? Split it, yeah, split it into its two components. All right, so the first thing you need to do is you need to find the right triangle. And the right triangle might be a little more tricky to see than what you think, but the right triangle in this case is right here. And this is going to be our angle theta. Okay? This is just a geometry thing. I'm not going to get into a whole lot of detail, but if this was angle theta, this is angle theta. It's a geometry, like, they complement. I don't know if I'm saying the right things there, but if I said that this is on a 30-degree, if this is on a 30-degree tilt, then when you draw the force diagram, this angle between there would also be 30 degrees. Okay, that just translates like that. You can do a proof to figure that out, but we don't need to do that. Okay, now we have, now Matteo said we need to split it into two components. Now, would it make sense to do a component that's here and here, or here and there? Where do we want the components to line up on?
X and Y.
The x and y axis, right? Because that's where these forces are. And once we have those on the x and y axis, we can start to say what things balance one another. So, here, all right, this one in blue. Here is one component. Here is another component. What will we call the blue component?
why?
F little g little y, right? Because it's the y component of Fg. And this one will be F little g little x. So this is saying that the y component of gravity is that blue, and the x component of gravity is the red. Now we can start to look at how do these forces balance. Does anyone see an equality on there now? Can someone tell me an equality that we have? Which ones are you looking at, Tim? Tell me the names of the forces.
Fn and Fgy.
Yeah. We know, let's go back to why we're doing this. We know that this is balanced because it's not accelerating. So there must be some balance in our force diagrams. And yes, once we break it into components, we can see that balance a whole lot clearer. This is equal to that because they point directly opposite of each other. Fn must equal Fgy. Now the other one might be a little more confusing to see, but without getting into a whole lot of detail about vectors, one thing we can do with vectors is we can shift them across like this. You can never tilt a vector, so we can never take this one and tilt it like that. But you can shift it anywhere you want, up and down on the y. So if we take this one and we shift it to right there, what do you see, Elizabeth? Which ones?
F G of X and F of friction.
Yes, exactly. The force of friction is counteracting the part of gravity that's pulling it down the slope. Let's think about, I'll just put one more. Think about that. What is causing, what force is friction opposing? It's a piece of gravity. It's not all of gravity, because if it was all of gravity, that's what all of gravity looks like. This is just a piece of gravity when it slides. Gravity's pulling it on a slight piece of gravity. The x component is pulling it down the slope, and that's exactly what friction is opposing. And we can see that right there. There's the pull, there's the friction. It's, yeah, it's opposing it right there. So we can write an equality that says the force of friction should be equal to the force G of X. Now, let's do one last rewrite. If we only know the angle and the force of gravity, we don't know these components yet. These are just substitutes. We need to write what they equal to using the angle and FG. So we need to think. FGY, is it our adjacent or our opposite side? It's our adjacent side. Which trig function goes with adjacent? Cosine or sine? Cosine. So you can always use that trick. If it's the adjacent side, it will just equal the hypotenuse, which is kind of hard to see, but this is our hypotenuse, FG times cosine theta. This one is our opposite side. Opposite always goes with our sine trig function. Will be FG times sine of theta. Bada bing, bada boom. There it is. We rewrote. Now we can say, if all I gave you, which was our original example, was just gravity and an angle, you can write the normal force in terms of gravity and the angle. Friction force in terms of gravity and the angle. Right? The way we can visualize it by splitting it into these components and seeing that balance out on the diagram there. Okay? If you guys caught a decent chunk of this, you should be proud of yourselves. It's a lot of work. It's really hard to get it the first time around. We're going to keep practicing this. And in order to do that, we're going to start with a little worksheet that I can hang out. We got about 5 minutes left of class, and you guys can start to look at this worksheet, okay?
I feel good. I think I don't need worksheet.